Welcome to the Nuclear Weapons 101 series, a compilation of short presentations on nuclear weapons-related topics. The goal of this series is to improve nuclear literacy across the Department of Defense and promote a greater awareness of the critical role U.S. nuclear weapons serve in supporting the safety and security of America and her allies. These presentations are produced by the Nuclear Science and Engineering Research Center, an office of the Defense Threat Reduction Agency located at West Point, New York. This presentation is entitled An Overview of Prompt Effects. The purpose of this briefing is to introduce the three principal outputs that rapidly follow from nuclear weapon detonations occurring within the Earth's atmosphere, as well as the general physics that cause them. An overview of these topics will better prepare viewers for future, more detailed presentations on each of these effects, as well as their associated phenomena. First, the term prompt refers to a brief time span beginning at the moment a nuclear weapon begins to detonate, and it typically applies to all weapon-induced effects that occur within the first 60 seconds thereafter. As such, the prompt effects of nuclear weapons are considered separate from the residual effects, which are much longer lasting and will be described in later presentations in this series. Second, this discussion focuses on the results of nuclear weapon explosions that occur at or relatively close to the surface of the Earth. So from altitudes of sea level up to around 30 kilometers or 100,000 feet. This is an important distinction because both prompt and residual nuclear weapon effects change significantly at increasingly higher altitudes, just as they do when nuclear explosions occur beneath the Earth's land and sea surfaces. Lastly, the three specific prompt nuclear weapon effects we will now briefly describe are the initial radiation, thermal pulse, and blast wave, which occur in the same order they are listed here. When a nuclear weapon detonates, it emits radiation in roughly all directions equally, primarily in the form of neutrons, gamma rays, and X-rays. Neutrons and gamma rays are produced predominantly as the weapon itself detonates, or while the nuclear fuel is undergoing active fission. This typically occurs in less than 1/10 of a millisecond, and these particles are emitted at very high energies, therefore traveling long distances through the air until they are eventually absorbed within matter, potentially causing harm to any people they pass through along their path. Additionally, many high-energy neutrons interact with the surrounding materials before they slow and are absorbed, such as the ground, buildings, or vehicles, which can result in additional gamma emissions or the production of radioactive isotopes within those materials, which may also emit gamma rays for varying amounts of time. Although quite dangerous, the summed energies of these neutrons and gamma rays make up just a small fraction of the total energy released from a nuclear explosion. In contrast, the X-rays produced from a nuclear explosion comprise, by far, the largest portion of energy released, roughly 70 to 80% of the total yield. As the weapon detonates and the nuclear fuel is consumed during the fission chain reaction, nearly all fission fragment kinetic energy is deposited locally, which instantaneously drives the internal temperature of the device to millions of degrees Kelvin. At these temperatures, the device is heated beyond a gas and into a plasma state, thereby liberating countless atomic electrons, and it is these free electrons that produce the immense numbers of X-rays. Consequently, though, when compared to the high-energy fission neutrons and gamma rays, the escaping X-rays are emitted at much lower energies, so they typically travel much shorter distances, often only a few centimeters to meters, before depositing all their energy into the surrounding air. However, this ongoing deposition of X-ray energy as the nuclear weapon detonates heats the surrounding air to hundreds of thousands of degrees Kelvin, thereby creating a fireball of burning air that expands outwardly faster than the speed of sound and drives the following two prompt effects. The extreme heat from the rapidly expanding fireball produces immediate thermal effects, including a large thermal pulse, which radiates outwardly from the fireball in all directions at nearly the speed of light. The thermal pulse initially departs the fireball at several thousand degrees Kelvin, but it cools as it expands outwardly, slowly losing energy. Thermal energy is just electromagnetic energy in the ultraviolet, visible, and infrared regions. So, unlike the much higher energy gamma rays or X-rays, these low-energy photons lack the ability to penetrate deeply into materials. Despite this, the energy intensity from a thermal pulse can still burn, ignite, or even vaporize exposed materials, depending on the material proximity and characteristics. The final prompt nuclear weapon effect is the blast wave. As with the thermal pulse, the blast wave is also produced by the nuclear fireball, specifically the extremely fast rate at which the fireball grows. Due to the ongoing X-ray emissions as the weapon detonates, the fireball initially expands outwardly in a roughly spherical shape much faster than the speed of sound, which thereby creates a dense pressure buildup along the outer edge of the fireball as the shock-heated air is pushed outwardly at a faster rate than it can naturally displace. However, the rate of fireball growth then begins to slow and shift to diffusive growth as the X-ray emissions conclude. As a result, once the outward rate of fireball expansion drops below the speed of sound, roughly 350 meters per second, a blast or shock wave separates from the fireball and travels radially outward in all directions at that speed. As such, the blast wave always interacts with objects after the thermal pulse arrives, and, just like the thermal pulse, the blast wave loses energy as it expands further from the nuclear detonation site. Nevertheless, blast waves produced by nuclear weapons are extremely dangerous and capable of flipping vehicles, destroying buildings, and damaging other forms of infrastructure if the overpressures are sufficiently high, a function of weapon yield and proximity. This concludes the presentation. If you would like to continue learning more about nuclear weapons and their effects, please click on the link below. Thank you for your attention.